All right, good afternoon, everyone. Let's get started. So we're going to start today with just the simplest possible machine learning problem that we can imagine. And we're going to go, as we go through the course, things will get more sophisticated, but if you guys feel like this is incredibly simple at the beginning, you're right, it is. But we want to be able to understand everything we do as clearly as possible, and that's why we're starting with something extremely simple and building up our understanding. So this first unit is what we call simple linear regression, and the word simple in this case means that we're only going to be predicting one scalar from one other scalar. So let me get into it a little bit more. So within every one of these units, we have a motivating problem that is based on some real data set. So in this particular unit, the data set happens to come from a data set that has to do with a bunch of automobiles and their different characteristics. And there's many different prediction problems you can make out of this, but we're going to try to predict miles per gallon from other characteristics of those cars. So, so part of what we do in these lectures is we go through and show you, how we actually do this in the code, and then part of what we do is some of the theory. So today is going to be a mixture of both, but we're going to start with some of the basic coding things. So again, the task is going to be predicting fuel efficiency in miles per gallon of a car based on other things like number of cylinders, horsepower, weight, etc. So all the code that you'll see in this this lecture you can find in this. This is a Jupyter notebook, the .ipynb. You can find this in the GitHub repository. The data we're using can be found on this University of California Irvine library, though I think that you can find it other places as well. And so first, let's talk about how we load the data in. This is always the first step of anything you do. Machine learning is loading your data. So within Python, there's a really nice library called the Pandas library, and this is what almost everyone uses for loading in data. And so these Pandas routines have tons of different options, and this is because data comes in tons of different ways. Every data set is a bit peculiar in terms of what's provided, what's not provided, what's missing, and so on. And so that's why there's a bit of complexity in terms of sometimes just loading the data can be kind of a pain. And so often when you're working with Pandas, some weird thing will happen. Maybe it'll be an error, or maybe not an error, but you'll look at what you get and it just doesn't make sense. And you want to just basically use Google as your friend. Just try to figure out, okay, what is this error telling me to do, or what about this data set that I'm loading isn't quite right. So Google is your friend, and that's going to be kind of a theme with a lot of the labs. Anytime you work in a new language that you're not familiar with, you're bound to get tons of weird errors. And rather than panicking or just waiting for someone else, often the simplest thing is just Google that error, and you can find lots of people explaining exactly what it is, and usually you can figure it out based on that. Of course, sometimes you can't, and then you can turn to your TAs or to me or to the discussion forums in the class to get some help. So anyway, back to this Pandas library. The main command that we're going to use to read in the data is called read CSV, and what this does is it creates an object. Basically, an object is just sort of a generic thing that we have in the software, and this we're going to refer to this as a data frame that's going to have three main components. First of all, there's going to be the values, which are just the numerical values from our data set. They're going to be in this NumPy format. NumPy is the sort of linear algebra package for Python. Depending on how your data is formatted, there may be some column labels, and they will explain the meaning of the different features in the data set, as well as some row labels. And let me just, when I refer to columns and rows, let me give you an example here. So this is a nice visualization of the data set here. As you go down these rows, each one of these is a sample of your data set, and as you can see, a sample is a collection of different things to do with one particular car. So here we have the name of the car, we have the model year, the acceleration, the weight, horsepower, displacement, cylinders, miles per gallon. So many of these examples makes up our data set. So when we refer to columns, we're talking about these things. We'll also refer to them often as features. And in terms of what we see here is we see there's the data values, which are these numbers or actually these strings. But then at the top, we have the column label, which explains what it is. So for this particular data set, when we did this read CSV command, we were downloading this from an internet address. But it turned out that alone did not give us the names of the columns. So somehow we found those elsewhere. Maybe at that data set, if we just viewed things in a web browser, you would see there'd be some description. You would see, oh, okay, the data is organized this way. And so we actually created this vector of strings here, and then we use those names when loading the data. So that's why these things showed up. So sometimes you have to do that. Sometimes you don't. Sometimes these things come automatically with the data when you download it. There's other things we told it. I don't remember exactly if all these were necessary to get it to work, but in that data file were things separated by white space or commas, or there's all sorts of different ways data can manifest. So anyway, maybe after some trial and error, we finally got it to load. And when we print out, this is the df.head, the head command. What it does is here's our data frame object. And not only does this object contain a bunch of data, but it also contains commands. And so when you do df head, and we're telling it 6 here, it's going to print out the first 6 rows of that data set. And we can look at it and we can say, yeah, that makes sense. Everything seems to be fine, so we probably loaded it successfully. Okay, any questions on so far? Okay, so just a couple other things if you've never worked with Python before. Python has many different packages that you have to manually import into your program. And so that's what's happening up here. So we're importing that pandas package. And then often you want to refer to the package when you run a command like read CSV is in the pandas package, but you don't want to type out the whole word pandas, so you can abbreviate it here as PD. So this is like the common abbreviation for pandas, and so then you do pd.readcsv, and it knows that the read CSV is actually in that pandas library. Similarly, NumPy, we're importing that as NP, and then later on we can do various numerical processing using np dot something. Okay, so that's mostly what I wanted to say here. So everybody good with this so far? Okay. Now, when you download a data set, one of the first things you want to do is just visualize. Yeah?
So the head command is not part of the panda package, it's just a Python command?
So because we're using this df dot, that kind of tells us what comes after it's looking into this, this data frame. So the data frame, I don't know if, so object-oriented programming, the idea is you can have an object that has many different components. Some of it could be like data objects, but others could be functional objects. So within this data frame, it knows about various functions. And so this function head says print out the contents of the data frame for visualization. And it does it in this nice formatted way, which makes it easy to read. So, okay. All right, so we want to visualize the data usually as one of the first things we do, because as humans, we're pretty good at noticing patterns visually. And this can often tell us whether something is just wrong or if not, like maybe gives us some intuition about the characteristics of the data set. So this data set, as you can see, has many different features or attributes. And so what we're going to do is we're just going to focus on 2 of them. We're going to focus on displacement, which is the size of the engine or the size of the cylinders in the engine, and miles per gallon. And we're going to plot, miles per gallon versus displacement. So let's see how we do this. So for plotting in Python, there are several libraries, but the one that I've seen most often used is called matplotlib. And this library of commands is written in the style of MATLAB's plotting commands. So if you're familiar with MATLAB, then the format of all these commands will be very familiar. So in order to import it, not only do you import this, but you import some sublibrary PyPlot with the abbreviation PLT, which is the common one. And then this last command ensures that in your Jupyter Notebook, when a new figure is created, it's in line rather than like popping out into a new window. Okay, so once we loaded this, the first thing we want to do is we want to extract the numerical values that are going to be used to make this plot. And so, in other words, the x values, which will be along the horizontal axis, and the y values. So one interesting thing about Pandas is that you can refer to these values by the heading of the column. So you can ask for, if you do df square bracket cylinders, it's actually going to extract all these numbers. You can also do it with a numerical index, like this would be index 0, index 1, index 2, and so on. But it's a little bit more natural to actually refer to these column labels. And so that's what we're doing here, and you can see there's just a couple ways to do it. In this case, we're doing this directly with this string MPG, and in this first case, just to show you a slightly different way of doing it, we're actually making the string into a variable xstr, and then we're accessing that column using df square bracket xstr. So in addition, once we get that particular slice of the data out, we're going to make sure it's formatted as a NumPy array. So we're going to wrap that thing with this NumPy array. And now this x and this y, we've made them into these NumPy objects, which will also come with all sorts of functions and other things we can do. And NumPy is just the default way we're going to work with data in Python. So this is a very standard thing, is any kind of numerical thing we have, we make sure it's formatted as a NumPy array, and we work with that. Okay, so once we have our x and y finally ready, we can use these plot commands. And again, if you're familiar with MATLAB, these will look very familiar to you. So plot x comma y gives us this plot, and then this is the marker we're going to use. We're going to plot every data point as a little dot. There's other commands in Matplotlib, like there's a scatter command that will give you a similar plot. In addition, we're going to make the plot a little bit more easy to read by putting an x label down here of our displacement and our y label of our miles per gallon, and we're going to plot these grid lines using this. Okay, so we can do this actually for not only displacement and miles per gallon, but horsepower miles per gallon and acceleration miles per gallon. So let's now just pause and take a look at these figures we created, and let's say that our goal would be to predict miles per gallon from either displacement, horsepower, acceleration. Which ones of these variables would work better? Which ones of these three? What do you think?
Like horsepower.
Horsepower, okay, and yeah, and why did you say that?
So acceleration doesn't seem very correlated. Displacement and horsepower both seem pretty correlated, but displacement normally has like a couple very like standard values, like 400 or 200 or 250. So you might have more variation within that, whereas horsepower is more continuous.
Okay, so yeah, so we're actually going to talk about correlation a little bit later today, but right now, I think there's many explanations you guys could have come up with, but basically, you want to see some sort of trend, and then you want to see that the values are close to the trend. Like the trouble with acceleration, you can see, is that things are very spread out. So no matter what trend I try to pick, there's a lot of deviation from the trend, which means that if you say this is my acceleration, it's just very hard to say based on this data what the miles per gallon could be, because there's such a wide range of possibilities, right? So, but anyway, this is kind of the first step, is just taking a look at the data and seeing what can we expect. Do we think that this prediction is going to be successful, or is it just sort of a lost cause? Okay. what about mathematical models? Can we say a little bit more about, let's say, again, horsepower? If you wanted to say that this follows some sort of mathematical trend, do you have any guesses of what that could be? Exponential. Okay, yeah. I mean, there's various things, maybe exponential or inverse. But yeah, you can imagine coming up with some mathematical model for some curve that kind of goes through your data. And that's the sort of stuff we're going to be talking about a lot throughout this course, is different models, how you deal with them. But we, in this unit, are going to start with the simplest possible model, which is going to be a linear model. Okay. So, but before we even get into those details, let's just try to build some language, some nomenclature for these general sorts of problems. And then we'll be using this nomenclature throughout the semester. Okay, so the very first thing is the variable we're trying to predict, we're always going to call this y throughout the course. So in that case, that's going to be our miles per gallon. That's going to be our y. And then the variable we're using for the prediction, we're always going to call that x. So that's x going in that direction. Now, there's a lot of names people give to that y variable. It kind of depends what field you're coming from and so on, but some of the more popular names are target, label. Those are probably the ones we're going to use most often. But then there's a few that statisticians use, like regressand or response variable, dependent variable. And it's important to know these different terms because sometimes the sources you go to when you read about things will use one of these, and if you're not familiar with it, you'll just be lost, right? So I'm going to focus on these throughout the lecture, but these other ones, especially these two, are definitely things you'll see. Similarly, for the thing we're using for prediction, I'm going to usually refer to it as a feature or maybe a predictor, but you'll also see it referred to as a regressor or an attribute or an independent variable. And another comment I mentioned before, in this unit, we're going to be considering that the thing we're using for prediction is just a single scalar value. In the next unit, unit 2, we're going to broaden that to a set of values, like a vector of values. But in this unit, we're just starting as simple as possible. And that's what makes it so-called simple linear regression, is just the use of a single one. Okay, so that makes our problem, one thing about it is it's very easy to plot because we just have x versus y, so we can make these nice plots. And what about our data? So our data is going to be a collection of pairs, xy pairs. And so when we talk about the data, we're going to put the subscript I. And I is always going to be the variable we use as we index through our data set. So in terms of like this table we saw earlier, I would be the index down the rows. Okay, so I is going to index over all our different samples here. And so the data we're given are pairs of xy. And we're going to use this n to refer to the size of our data set. So we're always going to use n for that. Okay. Number of samples. Okay. Yeah, and a sample, every one of these pairs is going to be called a sample. Okay. And then finally, this sort of plot we made on the right, this is called our scatter plot. Okay, so just a bunch of terminology. We'll get used to this because we'll be using all these a lot. Any questions so far? Okay. Okay, so I mentioned that there would be some blanks in the lecture notes. So here's where we start to see some blanks. So, okay, so the essence behind our linear model can be written in just basically one very simple equation, or maybe not an equation because it doesn't involve an equal sign, but an approximately equal sign. And the idea is we are going to assume the relationship that y is approximately equal to beta 0 plus beta 1 times x. And here we're talking about a generic x and a generic y in that pair. Now, I want to emphasize again the approximation. This is because we know that our data is not perfect, that yi is not exactly equal to this with the xi here for every I. But what this relationship tries to say is that there's sort of a linear trend in the data, and that can be visualized by this line on the right. So in terms of this model, you can see that if you set x to 0 here, then y would be equal to beta naught. So that's going to be the intercept. So here we have x, and here we have y. So when x is 0, we're here, and so the value where that line crosses would be, maybe I'll make it green. This would be beta naught. Right? And what does beta 1 tell us then, qualitatively in the picture? Beta 1 controls the slope, exactly. So and that's really, there's only two parameters that completely determine that line, right? It's the intercept and the slope. With those two numbers, I can make any line on this graph. And so my linear model is completely defined by those two numbers. Those are going to be called the parameters of the model. And we'll often want to just put them together into a vector. This is going to be a vector that has only two entries, beta 0 and beta 1. And we're going to use a boldface beta to represent that vector. So a couple other comments then. Throughout the notes, whenever we deal with vectors, we're going to use boldface notation. I think you probably saw that in homework 0 if you looked at it. Matrices will also be boldface. When I'm writing things down, because I don't have a good way of doing boldface, I will do something like beta with an underline to emphasize that it's a vector. And the reason why this is important is that sometimes in the course, if you don't identify what are vectors and what are not vectors, things can get very confusing. Because you might have like a vector of data points x, and then you might have like this generic scalar x that is sort of representing like what happens in general. And if you don't identify one as a vector and one as a scalar, and you have a bunch of math, it's really not clear what you're talking about anymore. So that's why it's in many cases really important to highlight which are vectors and which are not vectors just in the notation itself. Okay, so sometimes these parameters, betas, sometimes we call them coefficients or weights. Now you might ask, okay, why are we using this particular model? The main reason why is because it's easy. It's simple to work with. We can derive a lot of stuff in closed form. Once you get to more complicated models, you simply can't work with them that easily. As a human, you can program algorithms to work with them, and we will do that later. But for right now, we're just trying to get some understanding. So when would this linear model be a good model, do you think? And when would it be a bad model? I don't know, like maybe we can go back to these pictures. Would the linear model be good for any of these?
No.
Okay. Which one would it be maybe best for? Horsepower, yeah, I think so. The idea that we're probably all implicitly using is we're just trying to imagine how you could fit a line most closely to those data points, right? And exactly that whole fitting process is what we're going to get into next in the lecture, is what do we mean by fitting the line to the data. Okay, so there's going to be data sets like this particular data set here. As you can see, it's actually looks like it's a really good model. I don't even know how to improve it necessarily. But there's certainly data where it's not the best model. So, but still, it's something that people consider maybe just as a simple baseline.
I have a really quick question. Just
Yeah.
on notation, I've never seen this triangle over.
Oh yeah, sorry, I meant to talk about that too. So this triangle means a definition. And sometimes I want to distinguish definitions from equalities in the sense that, like, if I just define a variable, like here I'm just defining y hat as this, like you don't have to ask yourself, why is that true? It's just, I'm forcing this name on you, right? That's what a definition is. Whereas if there was an equal sign there and maybe y hat was something we talked about before, it'd be like scratching your head, well, why does y hat equal this? It forces you to maybe like wonder why am I calling that an equality? So sometimes, just to be clear, I'm putting that triangle, that definition. So I actually should have done one over here too, because here I'm just saying that, yes, there's these beta 0, beta 1. We established what those are. And now I'm just making a new thing, the boldface beta, and I'm imposing that definition on it. But yeah, that's a great question. And it also reminds me that I also need to talk about this y hat here. So what we said so far is that this is an approximate relationship between x and y, and we're sort of, that approximation is highlighted by the use of this approximately equals 2 sign. But let's say that I want to define the value that I reach on this line. So if you tell me x is 20, I want to give a name to the value predicted by this model. And that is exactly what that y hat is. So this is an equal sign. So if you tell me what beta 0 and beta 1 are, and you also tell me x, I can tell you exactly what your prediction will be, and we're going to give that the name y hat. And the hat is going to be used throughout the course to mean prediction. So y hat is, you're going to think of that as it's our prediction of y. Maybe later we'll have like beta 0 hat will be our prediction of some true beta 0, and so on. Okay, thanks for the questions. Anything else? All right. So, all right, so now we're going to get into this notion of fitting the data with our model. So as we said before, we don't have an exact prediction. We don't expect to have an exact prediction in that we're going to say y hat is approximately equal to beta 0 plus beta 1 x. And this approximation is important here. But sometimes, it's hard to work with approximations because it's not really clear exactly what we mean by approximation. So let's make this more explicit. Let's write y equals beta 0 plus beta 1x plus one more quantity, which is going to be, we're going to call the residual, epsilon. And now that we have the residual in there, we can have inequality. This is y is exactly equal to this. And in fact, what we've done is we've taken the difference between y and our prediction, and we've explicitly given that a name, okay? Given that a symbol, epsilon. So if you remember this part over here, this was our y hat. So now you can see y minus y hat is epsilon. And this is the general expression that we say, holds generally. But if we want to talk specifically about the data points we've collected, we're going to put little subscript i's on everything. So we'll have, y hat I equals beta 0 plus beta 1 x sub I, and so on. We can put an I on our epsilon. So now when we look at this picture over here, oops, I wanted to do red. So maybe I'll do green. So if I'm looking at that particular point, the deviation between our prediction, which is our y hat, and the actual data point would be our epsilon I, right? So we now have sort of a visual understanding of what these epsilons are. It's the errors from the prediction line. Okay, any questions so far? All right. So qualitatively then, how might we try to fit our prediction line?
Minimize the residual.
Yes, minimize residual. Now, we have to be a little careful because the residual can be negative, and if I minimize a negative thing, it just...
Absolute value.
Absolute value. So the absolute value is one option. What are there other options?
Square.
Squared? Yeah. So there's various options. We are going to choose the squared value because that is the one that ends up being a lot easier to work with in our derivations. So in particular, we're going to define this sum over our training data. We're going to sum over our training indices I of epsilon I squared. And we're going to say that's the thing we want to minimize, sum of squared errors or sum of squared residuals. And we're going to call this most often RSS. though it has other names in the literatures, SSE, sum of squared errors, sum of squared residuals. And there's a nice Wikipedia page. If you click this green link, there's a whole nice Wikipedia page on this guy. So in case it's confusing, here on the left, we're saying that RSS is a function of these parameters beta, but you don't see the parameters explicitly on the right. So remember that these epsilon i's are all dependent on the betas you choose. You can kind of visualize that here. As I choose different betas, I will choose where my line is, right? And as I choose where my line is, it's going to affect all the different errors. So we can even write this a slightly different way that might be useful. Write it directly in terms of our y's. We can write it in terms of yi, the difference between yi and yi hat, sum squared. Okay. And the value of the parameters that minimizes this RSS is going to be what we call the least squares fit. So maybe this least squares is something that you've seen in other courses. That's great if you have. It's a very generic thing that's used all throughout engineering and other fields. So geometrically now we can also have an understanding when we fit our line what we're trying to do. We're looking at the squares of all those distances, summing the squares, and we're trying to minimize that. So you can kind of imagine as you start to move your line, some of those errors get very large, and when you square them, they get even larger, and you're moving your line around to try to minimize that sum of squared error. Okay. So yes, and there's other options, like sum of absolute values is actually, it's a great option, especially if your data has outliers, meaning if there's a few values that are far from typical, the absolute value will actually be a lot more robust to those outliers. But the trouble is, it becomes very hard to work with it in terms of derivations. It's non-differentiable. All sorts of other complications arise. And so we are going to focus on this squared error as the easier option. And we'll see later that there's actually other reasons we might want to do this if we're working with Gaussian noise, and this is going to give us what's called the maximum likelihood model. But anyway, let's now just step back and reflect a little bit about what we've done. And what we've done is actually sort of just one example of a general recipe that we apply to machine learning problems in general. So we start out by assuming a model with some parameters, and in this particular case, we've assumed a linear model with the parameters beta 0 and beta 1. Then, let's say we've gone and gotten some training data, so we have all these samples. Now we also have to choose a loss function. We've chosen RSS as our loss, as our criteria for goodness in terms of fitting our model. And the last step is to find the values of beta that minimize this loss on our data. So that's the part we have to talk about next. And it turns out that for this simple linear quadratic problem, we can do all the derivations in closed form. For other problems that we're going to encounter later in the semester, it won't be that easy, and we're going to have to turn to optimization algorithms to try to find them for us. But for now, we don't have to worry about a lot of those things. Are there any questions so far? Okay, great. So as we'll see, one really efficient way to getting straight at this answer is to come up with a summary of our data and then to work with the data. And actually, a summary of data is just statistics. Statistics is basically just different ways to summarize data. If we summarize it in the right way, and meaning if we collect the right statistics, and it turns out there's only going to be 3 numbers we really need to worry about, then we can figure out exactly our least squares fit from that. So, and this is also going to help us to understand conceptually what the least squares fit is doing, what about our data matters and what about our data doesn't matter. So for this, we just have to review a few things from basic statistics, which you guys have seen many times, I'm sure. The first thing is the sample mean. The sample mean is simply if you have a list of numbers, let's say in this case we're talking about xi, and you just take the average of the numbers in that list, that's the sample mean. So you sum up all the numbers, there's n of them, so you divide by n. So we're going to do that for our feature x. We're going to call that x bar. And we're also going to do it for our targets y, and we're going to call that y bar. Okay. So basically, what these tell us is the average value across all our samples, all our feature samples, and this is the average value across all of our target samples. But we don't care just about the average. We also care about how much the data spreads around or varies from that average. And for that, we have the sample variance. So for the sample variance, what we're going to do is we're going to look at the difference between xi and its sample mean. We're going to square that, and then we're going to average that. And similar for the sample variance of y. Okay. So one comment is for those of you who work with probability and statistical averages, I just want to emphasize these are not expectations. Here, there's actually no statistical quantities, no random variables, I should say. We're going to talk all about random variables in a few weeks, but for now, these are just deterministic quantities, just lists of numbers, and all we're doing is averaging lists of numbers and computing, these sample averages. Another comment is that those of you who know a little bit about variance, you may notice that sometimes people use 1 over n here, sometimes they use 1 over n minus 1. We're going to talk about that quite a bit in Unit 3, but for right now, it's actually important for us to use this one with the 1 over n, which some people call the biased estimate, because that's the one that's going to match all the derivations we do. If we use the other one, the things we get in the end won't be correct. So we're going to focus on these particular definitions of the sample variance. And the last thing is the sample standard deviation. All that is going to be the square root of the sample variance. So I guess I don't even have to write it. So if you just write, here, notice that this is sx squared. If you just take the square off, you refer to that as a sample standard deviation. It has a similar kind of meaning to the variance, except this is a squared quantity, this is a non-squared quantity. So when we visualize data, so there's actually 2 data sets superimposed. These are histograms of some red data set and a blue data set. Let's first talk about the mean. What would the sample mean of the red data set be approximately? What do you think?
19. Oh, it says 100.
Yeah, I guess it says it. Okay, so both these data sets are calibrated so that the sample mean is 100. And that's basically, visually, it's just sort of the center of mass of the data. Okay, the sample standard deviation then is going to tell us, roughly speaking, how much the data varies around that mean. So it turns out, it says it here, it's roughly 10. And then for the blue data set, it's 50. And the thing about the standard deviation that's nice is because it's a non-squared quantity, it has the same units as the data itself, so you can visualize it. The variance is a squared quantity. It's a bit harder to visualize. So the variance would be 100 or, 2,500, right? So that would be, those are much bigger numbers. They don't really match up with these numbers. So the standard deviation is just much more interpretable when you're looking at the data. But conceptually, if I tell you one, you immediately know the other, right? They convey the same information. Okay, so here we can come back to our data set, horsepower versus miles per gallon. So what would you guess that the sample mean of X would be? And remember, X is going to be the horsepower. So based on this, if you just had to guess.
Around 100?
Okay, yeah, maybe around 100, something around 100. What about y bar?
25.
Sure, something like this. What about SX? Standard deviation of x.
50.
Okay, maybe. Something like that. And then standard deviation of y? Yeah. You can see kind of visualizing, it's just you take that average and then you look for how much spread there is around the average. So of course, we're just doing this visually to get a rough estimate. But we can actually compute these directly with code, and that's what we're going to do here. So we're going to use this numpy.mean, which, as you might imagine, all it does is it takes our vector. This x is going to be, remember we created this before, this is a vector of all our samples. This is just summing the samples and dividing by the number of samples, which is exactly what we want. We're going to call the result xm. And it turns out it happens to be 104.47, which is not far from our guess of 100. Similarly, for ym, we can do this the same way. And for ym, it ends up being 23.45, which was not far from our visual guess of 25. Now, there's a couple different ways to do the variance. So here we're xx is, sometimes it's another way people write sx squared. But there's a couple ways to compute this in the code. So one option that you could imagine is there's going to be a .var function out there, right? Probably it's there. The tricky thing about variance functions or standard deviation functions is that depending on the code base, you never quite know whether they're going to default to this one or this one. So it's a little bit dangerous to just use np.var, np.std without actually consulting the documentation and reading up to see which one of those they used. So sometimes it's just easier than looking up the documentation, just do it another way. Let's just use the mean command for this. And so what we're doing here is we're taking x, subtracting its mean, which we computed here. This is going to give us a vector of centered or mean subtracted samples. Then this star 2, what that means in NumPy is it's going to square each of the values in that vector. And now we're going to take the mean of those. And so we're just kind of in one line implementing this formula. And we're doing it in a way where we're sure we're going to have the right scaling. So that's why I'm doing that rather than using np.std or np.var. Okay, so, and these are the values we get, which are a little smaller than what we guessed, but hey. Okay, so any questions so far? Okay. So there's one other really important quantity that we need to know for doing prediction, because so far, if you think about what we've done, is we've looked at x separately, we've looked at y separately, but we never looked at the relationship between x and y in our statistics, right? Sample mean of x, sample variance of x, sample mean of y, sample variance of y. So the key quantity that we need for our linear regression is the sample covariance. And the sample covariance is going to be, so maybe not surprisingly, you're going to take xi, subtract its mean, take yi, subtract its mean, and then look at the average of that product. And so this is called the sample covariance. And it gives some sense of how related these two variables are. Now, related is a very generic concept. It's a very particular form of relatedness. There's other ways to measure how x and y are related, but this is, in some sense, one of the simplest. But there is something about this definition that's still a little bit complicating. For example, what happens if I compute the sample covariance and then I double all the values of x? What will happen to the sample covariance? It will also double, right? Same with y. If I double the value of y, the sample covariance doubles. So not only is the sample covariance telling us about how related x and y are, but it's also telling us about how large x is on its own and how large y is on its own. And with all those three things going on together, it's a little bit hard to understand maybe what it's telling us. So maybe it's better if we normalize it for interpretation. So when we normalize it in a particular way, we can take out the effect of the scaling of x and the scaling of y. And that's where we get this so-called sample correlation coefficient. So in particular, what you do is you take this SXY and you divide by SX and you divide by SY. And now, if you looked at this row quantity and you doubled x, it would not change. So this statistic is invariant to the scaling of x, invariant to the scaling of y. It really just tells you only about the relationship between x and y, which is a lot easier to interpret. And in particular, based on this normalization, it's guaranteed to always be in the interval between -1 and 1, never greater than 1, never less than -1. And so now this is very interpretable. So here are some pictures of different cases where rho xy, the sample correlation coefficient, ranges between 1 and -1. So yeah, how can we describe this? What about this case, rho equals 1? The picture is maybe a little bit misleading. What must be true about our data to get a correlation of exactly 1? How could you describe that?
It must be equal or linearly dependent on the
Yeah.
results.
So how would we describe that in terms of?
Same standard deviation?
So y is actually a linear function of x.
Yeah, they need to sit. The data samples need to sit on a line perfectly. This particular picture, I don't know. It's hard to tell whether they actually sit on a line or not. Maybe they do, but yes, if they would all fit exactly on a line, then they would have a correlation coefficient of exactly 1. Is it affected by the slope of the line? What if I made the slope a little bit less? Does the correlation? No. Right? So as long as the slope is positive, it could be any line. As long as the slope is positive, you're going to get this correlation of 1. Similarly, if it fits on a line with a negative slope, you're going to get a correlation of -1. Okay. Now, when that correlation coefficient gets closer to the origin, you get some spread around a line. And when you're exactly in the middle, there's absolutely no linear relationship between that at all. We say they're uncorrelated, but there's different ways that can manifest in terms of the pictures, the scatter plots, but here's one way that it manifests, where if you tried to do a linear fit of this data set, you would be completely unsuccessful. Maybe one way to think about it. Okay. Yeah.
Can I say that one way to look at covariance is that how linear the relationship between x and y is?
In a certain sense, yeah. So we'll see this will come back when we finally derive our least squares fit and we measure the final performance. We'll see that it depends directly on this rho xy. And that will be one way to answer your question positively. Yeah.
What would you get for 0 or vertical slopes?
I think you get 0 over 0. You get one of these undefined things. So yeah, you can't really say. Yeah. Okay. All right. Anything else? Okay. Great. So when we do our derivations, we won't see things exactly in this sort of form or exactly in the form that we define the sample variances. We will often see things in the form of this, or the same thing with y. So we would like to be able to relate that to our statistics. So that's what we're going to do next. We're going to come up with an alternative formula that's extremely useful that will come up a lot. And so let's just start by starting with our definition of sample variance of x we came up with earlier. And let's expand this quadratic. So we're going to have an xi squared term here. We're going to have a cross term, right? We're going to have 2xi x bar minus 2xi x bar. And finally, we're going to have an x bar squared term, right? So once we expand this into those three terms, then we can apply this this averaging operation separately to them. And when we apply the averaging operation to the first of those three terms, we get this. When we apply the averaging, maybe I'll just write this out. So we get xi squared minus 2xi x bar plus x bar squared. Okay, so when we average this over I, we can't really simplify that. When we average this term over I, we realize that this x bar is just a scalar in that averaging. We can actually move it in front of the summation, in front of the averaging, right? Same thing with the 2. So this is a little bit of a simplification where we're seeing here that the averaging is only on the xi. And then finally, we're going to get the average of x bar squared. But x bar is independent of I. So the average of that is just x bar squared alone. Another way to think about this is if I sum this up n times and then divide by n, I get the thing I started with. Right? So anyway, so after this little expanding the square, we get this equation. And we can go a little bit further. We can, let's see. So what do you notice about this? Have you seen this expression before?
That's the mean.
That's our x bar, right? So we have here x bar squared. We have minus 2x bar squared plus x bar squared, so we can combine those quantities to get the first term minus x bar squared. And now if we rearrange things a little bit and we just focus on the average of xi squared, we can get this important relationship that this equals the sample variance of x plus the squared sample mean. So this is a super important equation that shows up a lot. And it basically says, yeah, when you average squared values, there's really two components. There's the squared of the average value and then the squared of the deviation around that average value. Okay, so any questions on that derivation? Okay, so this is going to come back. We're going to use this often throughout the course. And what about the sample covariance? It turns out to be very similar. So what we can do is we can again expand that square, and we end up getting this. We get 1 over n times the sum times xi yi, that thing, minus x bar times y bar. And if we rearrange this, we can find that this, you could say the average of the product xi yi is the sample covariance plus the product of the sample means. Yes?
Why didn't we write the summation term in the variance as the mean of x squared?
Summation term.
So the 1 over n summation of x squared, isn't that the mean of x squared? Like if x squared bar.
Okay, let me see if I understand your question. So you're asking, is that just that?
No, this is x squared bar, not x. So the summation term adds up to x squared then bar.
X squared.
So it's the mean of xi squared.
The mean of the square, not the square of the mean.
Yeah, mean of the
The left side of equality.
This one?
square. Yeah, so
Yes,
this is
yes.
x squared bar.
Mean of
Yeah.
x squared.
Different notation.
Sorry, I'm being really dense. So are you saying that there's an error here, or you're just saying there's a different way of thinking about it?
Can't I'll give it a notation as x squared bar for this one as well.
Oh, I see. I see. X squared bar. It's I see what you're saying. It's not a notation I've seen, so I would not recommend using it because I think it could confuse people. Yeah, but yeah, conceptually I understand what you're saying.
What do these alternative formulas say exactly?
Well,
Why we are using this?
So one reason why we're using it is often when you do derivations, this term or this term will manifest. And then if you want to relate it to the statistics of x and y, it's very convenient to know that the average of the squared xi is the variance plus the squared mean. So this is something that will come up in derivation, but just conceptually, it's kind of, what happens if you average a squared quantity? What do you get? So that's, and then this is similar, yeah. So that's what we're saying.
Just like borrowing notation from stats, is that like on in the first red box, we have the left side of that, is that notated as SXX sometimes? And like how there's like the sum square errors or SSR, there's
So-
like SXX for
So this guy alone is sometimes written as SXX.
that one.
Yeah. So there's, yeah, yeah. Just for this course at least, we're not going to come up with a notational shorthand for this. We're just going to leave that as is, and then our notational shorthands will be these other things. In fact, I think the next page, yeah, so here's our summary of our notation so far. In addition to all the formulas, the sample mean, we're going to call that x bar. The sample variance, we're going to call that either S XX or SX squared. Sample standard deviation is just going to be either SX or the square root of SXX, and we know the equation for that, and so on and so on. And in Python, we'll try to stick to these, but there's obviously other variable name choices. So that's it for today. So next time we'll put these things together and we'll see how these relate to our optimal least squares parameters. So see you guys on Friday.
Thank you.